University of Waterloo. My name is Nancy Day. I'm a professor here in the School of Computer Science, and I'm here to welcome you and to be your host for today. So we have three wonderful speakers lined up to tell you something about computer science, and our goal today is to get you excited about the things that you can do if you learn about how to work with computers. So I'm going to start today. First of all, welcome to our webcast. We have some listeners remotely, so welcome to those people as well. We're going to start today with some words from our director from the School of Computer Science. David Taylor is here to welcome you as well.
Okay, good morning, everyone. As Nancy said, I'm the director of the school, and I'm really just here to welcome you and give you a bit of background, and then we've got three very interesting speakers for you through the rest of the day. So, first of all, I need to start out by saying that next week is Computer Science Education Week, and that's the reason for the scheduling of the event. Ideally, we would hold it next week, but just for reasons of availability of large rooms like this, we needed to pick a day this week rather than next week. So we're a little bit early, but welcome to those of you who are here in person, and welcome to those of you who are watching this over the web. So thank you for coming to celebrate Computer Science Education Week with us a little bit early, and we hope you find the day very helpful. CS Education Week is held in December because the birthday of Grace Murray Hopper, who is one of the pioneers of computing, is December the 9th, so it's just next week. And it happens that since I've been in computer science for really rather a long time, that back when I was an undergraduate, I actually had the privilege of hearing Commander Hopper speak in person when she visited the institution where I was doing my undergraduate work. And she was certainly a fascinating and inspiring speaker, but I'm sure you will find the speakers today, while they don't have the same history, people who will very much inspire you and show you why computing is a really interesting field as well. So our goal for today is, by the time you leave campus, we hope you're at least somewhat as excited as we are about computer science as a discipline. So while you may or may not right at this moment be really excited about computer science, it is clearly the case that computers are just all around us. They're almost literally everywhere. They're not just in desktops and laptops. You can find them in cell phones. You can find them in cameras. In fact, I was rather startled to read the documentation for my camera a number of years ago, talking about how the computer in the camera body talks to the other computer in the camera lens. And there's computers in microwave ovens, and it just goes on and on and on. And so we're using computers all the time for doing what at least now are everyday tasks, using social media, sending and receiving email, and for that matter, making popcorn in the microwave. So we're using computers all the time, but because of that, they're maybe not as exciting and mysterious as they seemed to be a number of years ago, and in particular back when I got started. My own interest in computing started around the end of elementary school, and I think it was because of an interest in problem solving and the idea that you could give a detailed sequence of instructions to a piece of machinery and that it would then actually do something useful and interesting because of what you told it to do. And the technology has obviously changed a lot since then. The first machine that I programmed there's some complications, but let's say roughly speaking it had 128K of memory on it. And now, I can't actually find it in my pocket, my cell phone, which is not really particularly well endowed, has about 65,000 times as much memory on it as that first room-filling machine that I used. And computers were really quite rare. I went to high school in Saskatoon, and I think when I was in high school, there were probably 4 computers in the entire city. And while that number may not be exactly right, I know if I go home tonight and do a census of the computers around my house, it will far exceed the number of computers in an entire city back then. But even though the power of computers, the ubiquity of computers has changed dramatically since I first became interested, I still find them really fascinating, the study of computer science and the things that computers can do for us. And in fact, when we're looking at theoretical computer science, the study of the things that computers can't do for us is just really fascinating. And I hope that the speakers today convey some of that fascination to you. And so while today is mostly about computer science in general, I think it's written into my contract that when I'm talking to a large group of people, I have to say at least a few words about computer science here at the University of Waterloo. We have some number of students. It turns out we've got so many programs that are different in different ways, it's hard to know actually how to go about counting our students. But clearly, by any measure, we have 2,000 plus students, and in fact, by some ways of counting, we have almost 3,000 students studying computer science here in the School of Computer Science. And we've got a lot of different programs. We have programs that allow you to combine an emphasis in computer science with an emphasis in something else. So in addition to straight honors computer science, you could study bioinformatics and look at computer science applied to genetics, to proteins, and to the processes that take place inside the living cell. Software engineering, a program that emphasizes software development and potentially leads on to registration as a professional engineer. Computing and financial management, I think the title pretty much describes what that is. And then finally, for the ambitious, if rather than studying for 8 terms and getting a degree from the University of Waterloo doesn't appeal to you, you could study for 10 terms and at the end of that get a degree from Waterloo and a degree from Wilfrid Laurier in our so-called double degree program in business administration and computer science. Here in the School of Computer Science, we're part of the math faculty, and I think it's something that's really quite astonishing that the mathematics faculty here at Waterloo is the largest concentration of math and computer science talent in the entire world. This is really a fairly special place. I'm very proud to be part of it. And the School of Computer Science itself has 80 faculty members working in 17 designated research areas and teaching in most of those areas as well. So if you come here to study, you can take courses in artificial intelligence. You can you can take courses in distributed systems, you can take courses in human-computer interaction, and you can take courses in other areas such as Professor Goldberg's and Professor Holmes back there, but they can tell you about those later on as well. So just as I close, I need to mention that Google has made a donation to help us put this on today, and we're very happy for Google's continuing support. I hope that you find the speakers throughout the rest of the day and your interaction with the other students to be very productive. And I'll now turn things over back to Nancy to move on with the rest of your day.
My own story for how I got into computer science is a fairly simple one because, you see, I'm the youngest of 4 children in my family. And if any of you are the youngest in your family, you know that trying to get your older siblings to listen to you or to do anything you want is virtually impossible, right? Okay, well, when I discovered computers, I was amazed because computers did what I wanted every single time I asked them. So that's why I got into computer science. And I like to borrow the words from Ed Lasowska at the University of Washington. He said, if you're creative, you love problem solving, you want to work in teams, and you want the power to change the world, learn about computer science. That's the kind of field you want to go into. All right, a couple of housekeeping things before we get started here. So we do have a microphone. This microphone is so that the people on the webcast can hear us. So if you have questions, one of our volunteers will be bringing you the microphone. Okay, so that everyone can hear that. Questions from the remote audience can be sent to an email address, and hopefully Heather has sent that email address to them. I'm not going to read it out now because I think it's a bit difficult to write it down. If you need to go to the washrooms are in the center out there. Maybe you've discovered them already. They're in the center between the two rooms that we're using today. Please help us keep this room clean. So if you have any garbage, there are trash receptacles and recycling receptacles at the back. We need you to keep your stuff out of the stairways for fire regulation, so your coats and your backpacks, please keep them with you. The exits, well, you came in some of them, and then there's also fire exits here at the front. Hopefully we won't need to know that. Your name tag has a colored sticker on it, all right? So everybody who's in this room should have a red colored sticker on it. That means you always come back to the red room, okay? So we have 2 groups going today, one in this room and one in a room across the hall. And you guys need to keep coming back to the red room, okay? The one that's on your sticker. And finally, if you have any questions today, you see these folks over here with the black t-shirts on that say computer science. They're here to help you if you need any assistance today, all right? So I think we're ready to get started with our first speaker. Our first speaker is Dr. Ian Goldberg. And Dr. Goldberg received his Bachelor of Mathematics from right here at the University of Waterloo in 1995, and his PhD from the University of California, Berkeley in 2000. He's now back with us at the University of Waterloo as a professor and a university research chair. and he's part of the Cryptography, Security, and Privacy Research Group, where he works on making software to preserve people's security and privacy when they use the internet. He teaches one of our first-year computer science courses, as well as our fourth-year computer security and privacy course, and he's going to be talking to us about perfect encryption. So please help me welcome Dr. Goldberg.
Okay, so good morning, everyone. Welcome to CS4U Day at the University of Waterloo. As Professor Day mentioned, I am Professor Ian Goldberg. I'm part of the Cryptography, Security, and Privacy Research Group, or CRISP, here at the University of Waterloo. So let's just do a little introduction to me. Who am I? So as Professor Day mentioned, I got my undergrad degree right here at the University of Waterloo. We actually have a number of faculty in computer science, faculty members who went to school here at Waterloo and liked it so much that later, when it was time to get a job, they came back. And I'm one of those. And I think Waterloo's a great place. As our director Taylor said, we are quite large. We have thousands of students studying computer science here at any time. And we have around 80 faculty members who teach computer science. And one of the really nice properties of having so many faculty is that their broad range of interests makes it so that we can offer a much wider variety of computer science courses than almost anywhere else. So if you're interested in different aspects of computer science, and you'll see, for example, 3 different research groups and areas giving talks today, if you're interested in a wide variety of different aspects of computer science, Waterloo is a great place to do that. So, got my undergrad degree. Bachelor of Mathematics is one of the degrees we offer. So my degree is in a double major in pure mathematics and computer science. And because we here at the University of Waterloo, computer science is part of the Faculty of Mathematics, you can do these very interesting combination degrees, not only the ones that Director Taylor mentioned between, say, business and computer science, but also between other aspects of mathematics and computer science, for example. And then I went on to sunny California and did my PhD there for a few years. Then I came back to Canada and worked in an industry research lab for a while before joining the University of Waterloo in 2006. So I've been here for about 7 years now. So what do I teach? There are 2 primary undergrad courses that I teach, and I'm really excited about both of them. I really love teaching both of these courses. So the first one is one of our first-year computer science courses, CS 135, which is called Designing Functional Programs. So in this course, we teach introductory computer science to both majors and non-majors that does it in a somewhat different way than you have probably seen if you've taken computer science in high school, for example. How many people have taken computer science in high school? Right, quite a few. I mean, you're here, so that's kind of a selection bias, right? So we teach introductory computer science in a quite different way than almost certainly you have seen in high school. And that's using something called functional programming. And with this way of teaching computer science, it focuses more on the underlying science, the underlying computer science, and the related mathematics than it does on the programming part. So of course you do program computers in this course because it's a computer science course, but the point of the course is not to teach you programming in some particular language, right? Once you're in university, we kind of assume that if we present you with a new programming language, you can probably learn it. Okay, there are lots of resources for you to learn a programming language. What we're teaching you is how to think about programming using computers. How to take a problem and take a computer and get the computer to solve the problem. And exactly what language you use, not so important. You can pretty much solve any problem in any language, but some languages are better at solving some problems than others. And in the first course in computer science, CS 135, we teach something called functional programming. And in the second course, we teach you imperative programming. And in the third course, we teach you object-oriented programming. And these are the three major paradigms of computer programming languages. So you see them in the first three courses. And as Professor Taylor mentioned, we teach these courses to something like 1,500 students every year. Between this course, the one for mostly majors and some of the non-majors, and the other two courses, CS 115 and 145, which are respectively strictly, 115 is strictly for non-majors, and 145 are for people who would like a bit of an extra challenge. Between these three courses, we teach them to about 1,500, 1,600 students every fall. Okay, so that's the course I teach in first year. The other course I really like teaching is a fourth-year course, CS 458, Computer Security and Privacy. And this is more related to what I'm going to be talking about today, as you could probably guess from the title, Perfect Encryption. So this is actually our single most popular fourth-year CS course at Waterloo. Something like 350 students a year take this course, and we offer it many times a year because we don't teach big rooms like this in fourth year. We try to keep the rooms smaller, and so we have to teach more instances of it, which is fine. So what is this course? Computer Security and Privacy basically teaches students how to identify security and privacy issues in the software they write, or the software they use, or the computer systems they design, right? Because students who graduate from Waterloo go on to have industry jobs, and often, unfortunately, having taken only one computer security course in your undergrad career will often at many jobs make you the security expert. This is unfortunate, but we have to teach you a lot about security because of this. Okay? So in this course, we teach you about how to make systems that are protective of security and privacy, right? And as a side effect, we have to teach you to recognize when programs and systems have problems with security and privacy. So for example, the first assignment often includes things like, here's a program, please break its security, right? Because you have to be able to recognize when a program is bad in order to write programs that are not bad. Okay? So what we're going to talk about today has to do with encryption. What is encryption? You have two people normally called Alice and Bob. So you have Alice and Bob, and Alice wants to send a message to Bob, or Bob wants to send a message to Alice. And there's an eavesdropper in the middle. Someone is listening to their communication. But Alice and Bob want to keep their communication private. Okay, so how do they do that? They use encryption. Now, encryption is an old technology. How old do you think encryption is? Yeah?
I would say probably it started since the 1980s.
Encryption started in the 1980s, says one person. Anyone else? Encryption started in Julius Caesar's time, which is about 2,000 years ago. Anyone else? Since the dawn of man. Well, the dawn of man predates writing entirely. So I think that's too early. So we have a bound now, the dawn of man and Caesar's time. Can anyone narrow it down a little bit? Okay, the first known use of cryptography was actually about 4,000 years ago in Egyptian times. Okay, so what kind of writing did Egyptians use? Hieroglyphics, right? You have the eye, you have the pyramid, the guy going like this, right? So what kind of encryption did they use? They just used non-standard hieroglyphics, right? They just wrote a different picture. So instead of the eye, they wrote the guy like this, and instead of the eagle, they put a cat or something, right? And because not many people could read to begin with, doing that simple change was enough to keep messages secure. Okay? Today, that doesn't work, of course, right? It's much harder to keep messages secure because adversaries, the person listening, can go to a lot of effort to break the encryption, right? So we have to use much stronger encryption methods in order to prevent an adversary who may have a lot of computing power from being able to break the encryption. Okay? As Professor Taylor said, just a few decades ago, the total amount of computing power in a city, or say that NASA used to launch things into space, is now dwarfed by the amount of power in your pocket, right? Probably most of you have a cell phone in your pocket or in your bag or something. That phone almost certainly has way more computation power than it took to send people to the moon. Yeah?
What about my cochlear implant as well?
Sure, your cochlear implant. I don't actually know how much computing power those things have, but almost certainly way more than any of these big computers from just a few decades ago, right? And even though these small computers are getting more and more powerful, computers are also getting bigger and bigger, okay? So here's a picture of basically a room full of computers. Each of these computers is way more powerful than your cell phone, right? So this room of computers has an awful lot of computation power. Okay? So you might think it's really hard to make cryptography that can't be broken even by big rooms of computers like this. And it's not only big rooms of computers, there's more technology coming that actually is very scary to people who do cryptography. And does anyone know what that is? Quantum computing. Here's a picture of a quantum computer, right? This is one just in our quantum computing center, just a couple buildings over. So we have a quantum computer. It may look big, but it's actually very small, right? A lot of this is just pipes and cooling and stuff. The actual computer is just a very, very small computer, and it can't do very much. We're not very good at making quantum computers yet. No one is. But people are working on it. And if quantum computers ever become bigger and easier to make and more available, that makes a lot of the encryption we use problematic and easier to break. Okay? So, what can we do about this? It turns out there's some very counterintuitive techniques you can use to make encryption that is unbreakable, even by huge rooms of computers or quantum computers or any amount of computation power. Okay? That seems too good to be true. And here's the next bit that's going to be even too-er gooder to be truer. Right? Which is that the actual encryption method you don't need a huge computer to do. You can do it without a computer at all, and that's what we're going to do today. We're going to send encrypted messages that are unbreakable even by quantum computers or rooms full of computers. Are you excited? Does that sound cool? Okay, so every pair of you has a packet. So now open the packet. Okay, in the packet, you should have 2 papers that look like this. Is that true? I hope the packets have been constructed correctly. 2 pages that look like this. Each of you take one. So these are the instruction pages and the worksheets. So each of you take one of these. Okay? You should also have 2 pages that look like this. Each of you take one of these. And you should have 2 transparencies that look like this. Each of you take one of these. And you should have 2 pens. Each of you take one of these. You see how it works, okay? Now, if you look closely at this piece of paper, you will see at the bottom there is a number, okay? That number should match between your 2 buddies. If it doesn't for somebody, please tell us. But that's what's supposed to have happened. It should match between your buddies, okay? But no one else has that same number. And how it's going to work is that only people with that number will be able to read the messages you send. No one else will be able to read the messages you send, even if they have a quantum computer or a room full of computers. Okay? And you're going to do this with a Sharpie and paper and transparencies. Okay? You will not use any computers to create and encrypt your message. This seems crazy. How is this going to work? Stay with me for the next 45 minutes or so, and we'll show you. Okay, so the first step is to come up with the message you want to send. Okay? For simplicity, we're just going to use these 8-segment displays like you would see on a digital clock. Right? People still see digital clocks now and again. It's not always your phone. Yeah, so they have these 8-segment displays here. Or 7-segment displays, rather. 7-segment displays. So what we're going to do is come up with a message and fill it in here. And the way we're going to fill it in is by taking your Sharpie and blacking out any segment that does not correspond to the letter you want to show. Okay? So I'll give an example. Now, with these displays, unfortunately, for simplicity, we just did these 7-segment displays. If we had more time, we could have done something more elaborate. Unfortunately, although you can show all numbers with these displays and you can show a lot of different letters, some letters are very hard to show with a 7-segment display like this. For example, K and M are really hard to show. So you have to kind of fake it, right? So you might just decide, for example, that K you might show with a symbol like this. It doesn't really look like a K. And M you might show with a symbol like this, which doesn't really look like an M. But most letters you can figure out how to draw. Okay? So let's say I start filling in the worksheet. You can see me filling in the worksheet there? There you go. All right. So I'm going to fill in this segment with my Sharpie, and this segment, and this segment. Okay? And what letter have I drawn? C. What's the next letter I'm going to draw? There you go. How do I do that? What segments do I fill in with the Sharpie? Top right. And what? Bottom left. Okay? And what's the next letter I'm going to show? 4. You figured it out, okay? So what segments do I fill in? The top. And what else? Bottom left. And what else? The bottom. Okay? What do I do next? So what do I fill in? The top and the middle. Okay? And I can continue in this fashion, and I do the Julia Child thing. There we go. And I pull the finished turkey out of the oven, and I filled in CS for you day. Okay? So go ahead and create the message you want to send. Right? It could be the easiest kinds of messages to send are, of course, numbers. And you have 16 characters here to work with. I just used 8, but you can use however many you want. Yeah, question? T is one of those hard letters, so you might do a T. So let's call this a K. Let's call this an M. A T you could do maybe like that. No, let's call that a T. If we were doing this for real, of course, we would have better than 7-segment displays, but it would take too long to do the activity, I'm afraid. Are most people done their messages? Now we're going to encrypt them. Okay? We're going to encrypt our messages using only a Sharpie and these non-computer items. Okay? Explain. So now's when you take your other 2 pieces. You're this piece, which is your encryption key, and you're this piece, which will be your encrypted message once you fill it in. Okay? And what you do is you line it up, put it on your desk like this, with the words over on the left. Okay? And then take your transparency and line it up on top of your sending key. Note one says sending and one says receiving. So line it up on top of your sending key and make sure the words are not backwards or anything like that. Okay, so it should look like this. The words on the left, and you can read them. Okay? Now you're going to be drawing on the transparency, not on the paper. Okay? So be sure to do that. Make sure to draw on the transparency. So the next tricky bit is you have to line them up just right. Okay? But don't do it yet, because I want you to look. So take the transparency off for now, and just look at what is underneath. Okay? So what do you see here? You see a bunch of funny looking 8s. Right? What's funny about them? Only half of each, right? So each of the segments has been divided in 2, right? And if you look at your transparency, you can see that clearly. Can you see that clearly? Yes. Right? If you look at your transparency, you can see that clearly. Each of the 7 segments has been divided in 2. Right? And in the key, what happens is in each of the 7 segments, one of the halves is black and one of the halves is white. Okay? And it's random. Every piece of paper we printed out has a random selection of which half is white and which half is black for each of the ones, right? So yours right? See here, this is different from this. I mean, some of them will happen to be the same just because that's how randomness works, but look at the bottom one, these ones are different here. But you will, if you take a careful look, you will notice that your sending key matches your partner's what? Receiving key, exactly, right? So only someone with the right key will be able to receive your message. Okay? So here's how the encryption works. What you're going to do is take your transparency and for each of the 7 segments in each character, you're going to fill in exactly one of the 2 halves. But which one will be very well specified, right? I'll tell you which one to fill in. Here's how to do it. You overlay your transparency on top of your sending key, like I said before. Okay, so line it up very carefully. You should be able to line up the thin lines, right, like this. Okay, does everyone see how that's done? Okay, now, here's how the encryption works. For each segment, remember, you're going to color in 7 half segments on each character. Okay? So we'll start with the first character, and we'll start with the top segment. Now, do we color in this half or this half of the segment? Here's how you decide. You look at your worksheet, okay? And you see, is that segment white or black? If it's white, you color in the same segment that is already colored in by the key. All right? So in this case, for me, the bottom half of the top segment is colored in, so I'm going to color in the same half. Okay? Then I look at the top left one. That's also white on my worksheet. So again, I color in the same segment. Right? And you see the reason I do this is so that the white still shows through. Right? Then I go to the top right. That's black on my worksheet, so what do you think I do? I color in the opposite segment. Right? That would be this one. Or the opposite half of the segment, to be more clear. Right? And similarly, the middle one is black, so I color in the opposite. And the bottom left is white, so I color in the same. And if you forget these rules, you can either figure them out, or they're written on your worksheet. The bottom right is black, so I color in the opposite. And the bottom is white, so I color in the same. Okay, so now if I take the key away and you just look at what I colored in, you'll see that in each of the 7 segments, let me zoom in here. I think I can zoom in. Woo! Okay. So in each of the 7 segments, I've colored in exactly one of the halves. Right? But if I overlay the key and the message, you see the letter C. Right? Okay, so any questions about that? So go ahead and start working on that. Okay, so remember, for each of the 7 segments, you'll color in exactly one of the halves. If you want it to be white, you color in the same half as your key is already colored in. And if you want it to be black, you color in the opposite half. And then notice there's a line here for message number over at the left. Write in your copy over the sending key number. Okay, so I would write 1A here. Okay, so a lot of people seem to be finished or finishing. So now, obviously, what you're going to do is take your this. Don't forget to write the message number on it and swap it with your buddy. Okay? Now when you've received this from your buddy, of course most people have figured out what you do is you overlay it on the receiving key side. Right? So here's your buddy. And you can see the message. Okay? But try something different. Take the message you got and overlay it on the wrong side, on your sending key side. Right? And what do you see? Random nonsense. Right? And this is part of the reason why these messages can't be broken even by the most powerful computers. So here's another example. Let's say I received this message from my buddy. Okay? If I decrypt it with the correct key, if I decrypt it with the correct key, what do you see? Hi, Alice. But let's say I decrypt it with the wrong key. Right? What do you see? Random nonsense, right? So why can't the adversary, they have all this super powerful computer, why can't they just try every possible key until they come up with a meaningful message? Yeah. Sorry? That's the thing. So he said they don't know which message is correct. It turns out the same message, note I haven't changed the message, if I decrypt it with a different key, let me make sure it lines up properly, I get the super secret message, over 9,000. Right? And if I decrypt it with yet a different key, I get the super secret message, 2 smiley faces. Right? You see? Yeah, smileys. Oh, it's off the right edge. Anyway, right? So the reason that this encryption is perfectly secure, it's perfect encryption, is that even if the adversary tried every key, they would just get every message out. And the adversary would have no way of knowing which is the real message and which is smiley faces and which is over 9,000 and which is every other possible message. Okay? So has everyone done the exchange? Okay? And now you might try swapping your message with someone not your buddy. Okay? So try swapping your message with someone down the table and try to read the message. You just made encrypted messages that even the most powerful computers that do or can ever exist cannot break, and you did it with a Sharpie and no computers. Now, of course, if you had a computer, you could do it faster, right? A computer and probably no Sharpie, right? You could do it faster, but the principle would be the same. So we now know how to make perfectly secure encrypted messages. But, so why don't we use this? Why doesn't all encryption on the internet use this transparency and paper method? Well, okay, we wouldn't do it with transparencies. We would do some digital equivalent. Yes?
The method is only perfect if you can ensure that the key is kept a secret.
Okay, so there are, in fact, a couple of different problems with this scheme that keeps it from being used widespread on the internet. One is the key has to remain a secret. The other is the person you're talking to has to have a copy of the key. Right? So when you buy something from Amazon, right, the first step, of course, you have this encrypted conversation. You've probably seen the lock or the green bar on your browser or something, HTTPS, right? That means it's a secure conversation. Right? So whenever you're about to buy something from Amazon, the first thing you do, of course, is you drive to Seattle and you hand them a copy of a key. Right? Everyone does that? No, you don't do that? No, we don't do that. right? Because that would be really annoying, right, to have to exchange copies of the key. The other problem with this perfect encryption is that you can only use it once for any key. If you send another message with the same key, you've lost all security. And now an adversary can actually read both messages if you send two messages with the same key. So it's actually very hard to use this kind of perfect encryption securely. That said, it has been done. And in fact, it used to be done by militaries and spies. So spies would get their orders and send back their reports using a system very much like this one. Okay? And they didn't have computers, and they didn't need computers. This is back decades ago. Right? They would use a system very much like this one to do perfect encryption. But there was one time when the Russian spies accidentally used the same key twice, and the American government was then able to read both messages because of that. Okay? So you have to be very careful when using this kind of perfect encryption, right? The keys have to say secret. The person you're talking to has to have a copy of the key, which is sometimes difficult, and you can never use the same key twice. So if you want to send a bunch of messages to your buddy, you have to start off with that same number of keys. Okay? How do you exchange that same number of keys? You have to go meet in person or something and hand them securely, right? But then why can't you just give the messages at that time? No, why can't you? There's a reason. You're in this room with me now, and I've handed you a bunch of keys. Okay? Now we can go away. We can go our own separate ways, and now you can send me encrypted messages. Right? So this method of perfect encryption allows you basically to time shift your meeting in person. So if I meet with you in person now, but you don't know what the message is now, you'll know the message later. I can share with you the key now, and later you can send me the encrypted message that I can read. Okay? But we still don't do that with Amazon, because we never have driven to Seattle and handed them a copy of a key. So how do we do that securely? That's a whole other topic that we won't be talking about today, but that's called public key cryptography. And that's a really interesting topic, but our time is up, I'm afraid. Okay, thank you very much.